guys. We'll get started. Has everybody seen that the grades for Rakesh's exam are now posted? Everybody see that? Yeah. Everybody passed this time? Yeah. Okay. So on Monday we had a little bit of look at a couple of phenomena. Okay. Where we can observe crystal growth and transformations or reactions based on kinetics. Okay, so the first thing that we looked at was crystal growth. All right, and we spoke about the process of where our atoms or molecules have to first diffuse through our liquid or our primary phase to the surface of a growing nuclei. Often we're going to have to attach to that surface, which involves a little bit of energy as well. Diffuse across the surface and attach themselves to a low energy site if they have time. Okay, and again, the driving force for this entire reaction is the whole concept of something like undercooling. All right, if that driving force is high enough, then these types of diffusion and placement processes into our kinks or steps or edges don't have enough time to proceed, and we get rapid growth, typically in certain directions. This is how we get structures such as needles or plates or dendrites in our transforming material. All right. We also spoke about how other sites within the crystal structure, all right, defects such as dislocations or vacancies, can act as growth sites or the onset or nucleation sites for grain growth. Okay, continuous grain growth. All right. There's a couple of examples there of different types of grain growth, spiral growth, birth and spread type growth mechanisms. Okay. Then we had a little bit of a look at our time temperature transformation type diagrams. Okay, we had a look at the solid-solid type transformations that we see in steels. Okay, in steel's TTT diagram, where we can, based on our cooling rate and the temperature at which we're sitting, and the time at which we're sitting at that temperature, we can instill different types of microstructures in our material. And those different microstructures are giving us essentially different mechanical properties. So depending on what our steel is going to be used for, we would prescribe a specific heat treatment based on these types of diagrams to our material. Right. We also had a look at the more basic transformations between the liquid crystallizing, and what happens to the vitreous solid if we're raised above our glass transition temperature. Okay, so the key examples there were things like silicate glasses, amorphous polymers, and metallic glasses. Okay, we did focus a little bit on metallic glasses. Okay, and how nucleation and growth of specific types of metallic liquids. Okay, competitions between thermodynamics and kinetics. Okay, the viscosity of the liquid, the packing efficiency of the liquid all affect nucleation rates, which in turn affect the rate at which the new phase forms and grows. Okay. We also had a little bit of a look at processing of these materials and how this is also a nucleation and growth defined step. Okay, basically if we have a vitreous material, PET plastic bottle, a silicate or modified silicate glass, we really actually do only have a specific amount of time which we can heat our material up above our glass transition temperature, do our forming activities and cool it down before this material crystallizes and its properties change. Okay. So utilisation of the amorphous structure in the supercooled liquid state for forming processes is something that's used by industry commonly today. All right, plastic bottle that you're drinking out of, everything else. Okay. All right. So with that, we'll move on to what we're going to be talking about today. All right. And that's recrystallization. All right, just back up there. Recrystallization. Right, so we've looked at changes of state between different types of phases or different chemical compounds and things like that. How their nucleation and their growth is affected by certain things. Typically it's this undercooling driving force or something in this manner. Interfacial forces between the forming phase and the existing phase. Okay, recrystallization is a little bit different, because what we're doing with recrystallization is forming the same phase within a phase, okay? But the structure of the recrystallized grains has a lower energy, a lower structural energy, which again, lowering structural energy is the aim of any material in nature, okay? Trying to lower its energy state. So let's have a look at recrystallization. Crystallization is actually a very important industrial process for metallurgy and some other key operations. Okay, so we've learned so far, okay, nucleation is the first step in the formation of a new thermodynamic phase or structure, and nucleation is defined to be the process that determines how long we wait before the new phase appears. Okay, classic types of nucleation. We looked at that using classic nucleation theory, where the driving force for nucleation is associated with the difference in the free energy between the two phases and their interfacial energy. We're about to learn that's a little bit different for recrystallization. Okay, so I won't worry about asking you the question because I've already half answered it for you. All right, but what is recrystallization? Just a definition here. Okay, so recrystallization is the process by which deformed or high energy grains within a material are replaced by a new set of defect-free grains of the same phase type as the parent material or a lower energy structure. Right? So these nucleate and grow until the original grains, these highly deformed grains that we're going to look into, have been entirely consumed. Okay, so it's kind of like hitting the reset button on a piece of material that we've deformed heavily and put a lot of defects into. Doherty's definition, okay, particularly in terms of metals, the formation of a new grain structure in a deformed material by the formation and migration of high-angle grain boundaries driven by the stored energy of deformation. Okay. So keep that one in mind as we go forward. Okay, the stored energy of deformation is essentially our driving force here for the nucleation and growth of recrystallized grains. All right. So here's a question I will ask the class. Why would a material want to recrystallize? You want to think of a good reason why a material might want to recrystallize? Said it already. Yeah. Anyone? Go on. Have a crack. Sorry?
Nucleation.
Well, that's probably the mechanism, okay, of why it would recrystallize, but why will it want to recrystallize in the first place? So I've answered it a little bit earlier on, okay. Basically, the material wants to recrystallize because it wants to lower its energy, its free energy. Right? If we take a metal, we go out the backyard and beat it with a hammer, okay, yes, we generate a lot of heat, and that heat's dissipated, but we're also storing energy in that material through deformation. Okay, and that stored energy is in the form of vacancies, dislocations, or extra grain boundaries that we're creating by breaking up the grain structure through that deformation process. So during plastic deformation, the work that we perform on a material is an integral of the stress and strain of plastic deformation, so permanent deformation. Elastic deformation, we're not going to get any recrystallization. All right? So although the majority of the work is converted to heat in working processes, okay, so you know yourself if you grab a piece of wire or something and you bend it multiple times, okay, it does get harder and stronger, work hardens because we're putting deformation in there, but the other thing that happens, it gets hot, yeah? You bend it enough times, you might burn yourself. So most of that energy is converted to heat, but some work or energy is retained in the material structurally as defects. So as I've said, by deforming the material in our crystal structure that might have been perfect, okay, we're deforming it, we're stretching it, we're bashing it, okay, we're putting defects into it. Vacancies, dislocations, we're refining the grain structure, grains become smaller because we're breaking them apart. Once we have extra grain boundaries, okay, there's also energy associated with those extra grain boundaries. Okay. So, for example, excess grain boundaries, atom site vacancies or dislocations. So these are the three key types of defects that we're instilling in our materials, okay, when we're deforming them. Okay. And all of these structures or defects, structural defects, are increasing the structural energy of our material. Okay. So that material wants to get rid of them if it can. So the rearrangement or the elimination of these defects will reduce the internal energy of the system. Hence, a thermodynamic driving force exists for the process of recrystallization. Material wants to reduce structural energy. To do that, it has to get rid of these defects. This is the reason that a material wants to recrystallize. Okay, so in terms of where you're at with your program, you haven't really come across dislocations, I guess, at this point in time. Okay, so I think it's Maths 3001 deformation mechanisms. I think you'll do with Paul Munro and Judy teach that course, and you'll learn all about dislocations. Okay, but basically a dislocation is a defect in our crystal lattice, okay, that allows deformation to occur. We've got some movies here which we'll have a little bit of a look at. Okay, the first one here is a bubble raft movie, and I'll try to pause it and explain it as we go if you're not familiar with what a dislocation actually is. Okay, it's not what happens when you fall off your bike and have to go to the hospital. All right, let's have a look. Let's try and have a look. Okay. Happens every week, I guess. So yeah, I shut down my laptop in my office, which is right there, okay, literally 20 meters away, and for some reason moving from that site to this site, it wants to re-log on to all of my applications that I've got open on my desktop that use internet. They each count as a login to the system and it locks me out. Great system. So Telstra to the rescue. Okay, I'll just hit pause here. What this experiment is a bubble raft experiment. Okay, and here the bubbles that are sitting on the surface of our liquid are meant to represent atoms. It's actually a pretty good analogy. All right. What you'll see in these bubble raft things, so all the bubbles are the same size, representing hard spheres or atom hard sphere type models. Okay, and you'll see as the surface of the liquid is disturbed that these bubbles are going to try to line up, okay, in a certain way and create basically a close packed plane in a crystal lattice. Okay? But you'll be able to also see where there's groups of these bubble rafts that are behaving independently, forming something like a grain in material. Okay? So you'll see essentially grain boundaries around these areas, okay, where those atoms are all a little bit random. You'll also see when the surface is disturbed greatly, start to impart things like dislocations into the material, so defects. You'll also see vacancies where there is no bubble in a particular hole. All right? And then finally, the last part of this little demonstration is they completely disturb the water surface. Okay, so we have a very, very messed up bubble structure, but very quickly, initially very quickly, those bubbles start to rearrange themselves, get rid of all of those defects in their ordering, all right, to form grains again. And those grains will slowly, over time, grow and remove all those defects that we see in the bubbles. Okay, so let's have a look. Okay. Missed it, but we'll just pull it up. Okay, so here's what I'm talking about. You can see all of our bubbles are lined up at this 60-degree array, which is the same as what would be occurring in an FCC material on the close packed plane. Okay, you can see regions that have got a common lattice structure, okay, and then you can see boundaries between other regions. These would be like our grain boundaries. We can see here defects in our structure, okay, holes or vacancies, okay, and then we can also see a series of defects within a grain. This would be similar or akin to a dislocation. A dislocation is basically a plane of atoms or a row of atoms, okay, within the structure that are half an atomic plane spacing away from where they should be. Okay, so these are our dislocations here, and you can see as they're stressing the structure, these dislocations move. So this is how dislocations actually do move in a crystalline metal material as well. As we deform it, for the structure to be able to accommodate that deformation, okay, these atoms have to literally shift over an atomic plane at a time to accommodate the deformation. That's what happens with these dislocations. Okay, an atomic plane defect will run from one side of a crystal to the other side and then essentially change its shape. Okay? That's what deformation is in a crystalline material. Dislocations running through the material will change the shape of the grain and the overall material. Dislocations can annihilate each other too if they're opposite in direction, but that's probably more something for Max 3001. And we can also see that vacancies can be removed by dislocations of the material. Okay, so this is the one we're interested in. Okay, so just have a quick note of what the structure is before deformation, i.e. person stirring the crap out of it with this stirrer. Okay, so before deformation. After deformation, we'll just take a quick look at it. Okay, so we can see here large scale defects, a lack of any crystalline structure here or repeated order for reference over here. Okay, so this is our deformed, heavily deformed region. Okay, and we can see the material recovering all on its own, trying to reduce the surface tension in this case. Okay, and over time, you'll see these boundaries and things, defects, here's our time lapse, start to disappear. Alright, so it's very quick at the end there, we might just have a quick look at it again. So over time, all those defects begin to disappear and annihilate one another, because it's a high energy structure. The system's trying to reduce its structural energy by eliminating these defects. So essentially what happens, all those small grains and defect regions disappear over time to reduce the structural energy of the system. Okay, so that's the bubble raft analogy. That's probably a good one to learn, right? Or it's going to help you to understand what's actually going on with the material in terms of recrystallization and further down the track when you start learning about dislocations. Okay, what does this actually look like in a real material? We've had a couple of looks at recrystallization in our earlier lectures, but I quite like this one here. Okay, so this is heavily cold worked copper. All right. Now, what we can see here are our prior grains of our material. So here's one big grain here. This is another big grain here. Here's another one here. These are prior grains. These things have been deformed very, very heavily. So you can see a lot of internal structures in the material, things like twins, micro twins. Okay, and we can see that within these large grains, other grains have started to form. All right. So we've beaten up these big grains and started to break them apart. All right. Everything's still in contact. It's not like breaking apart a brick or something like that. Okay, but we're refining the grain structure through all of this deformation. So this is a very messy structure. We can see here, now this material has begun to be heated. This is in an SEM, and we're watching it live. Okay, here are some fresh recrystallized grains. So straight away you can notice that, okay, we've got some color contrast there. That's related to the orientation of the crystal. Okay, here's another one here that's a slightly different orientation. But inside of the crystal, there's none of this messiness or crap going on. There's no twins, there's no dislocations or anything in these new structures. So these are our recrystallized grains, okay, and they're growing from these heavily deformed grains. Okay, so over time lapse, we can see gradually all of our deformed structure is overtaken by these recrystallized grains. Okay, and once they start to run into other grains, the growth rate of these recrystallized grains starts to slow down. Okay, they're getting impinged by the other grains. Okay, so if there's enough deformation in our system, we can nucleate and grow these recrystallized grains. They will grow quite quickly once they've started to form. All right, and then it'll slow down a little bit once they start to run into other recrystallized grains that are trying to grow. Okay. This last one here is one that you've already seen before of the cold rolled aluminium structure. So I won't play that one again, but you can go back and have a look at it in your own time. Things to take away from that one. You can see the high directionality of a rolled structure there. All the grains are lied down and elongated in the same direction. When the grains are recrystallized, however, all that texture is then lost. We'll play it. Okay, so we've seen it before, but we'll show it again. Okay, so here's our directionality from pre-rolling. We can see these large grains taking over the entire structure and growing again. So within these new grains, okay, there's no deformation, there's no dislocations or vacancies. They're a lower energy structure. Okay, so after and before. Okay, so with that information, we'll ask the next question. So why might we want to actually recrystallize a material? So we know why a material itself wants to recrystallize. It's trying to reduce the structural energy. Why would we want to recrystallize that material or have control over this process? Anyone think of a reason? Yep.
Wouldn't it just make the material stronger since there's less of the deformance?
Okay, you're on the right track, but probably flipped. So when we heavily deform a material, yes, it's got extra structural energy, okay, and it's now going to be harder or stronger than the original material. Okay, this is just basics of the stress strain curve. We know what stress strain curves are. You remember? Again, this is probably one of Judy's courses. All right. So stress strain. Okay. Here's our material. Elastic regime. Typical plastic regime. Yeah? So when we roll our material, we've always got our elastic regime that we will cover. Okay? But if we're going to be doing some cold rolling or something like that where there's been no recrystallization or recovery, basically, if we do our deformation, start to plastically deform, say we stop here, our rolling process. Okay? What are the properties of our material at this point in time? We translate our elastic region here. Okay? So basically, here in the undeformed space, we had a material that has a yield strength here, YS, okay, and an elongation or ductility of this, large. When we work our material, we follow our stress strain curve. We stop here, we've now got a material that has a strength here, and yield strength, okay, but it only has a ductility of this. Okay. So through deformation, right, this is what we're doing to our material. Okay. So deformation, something like a cold rolling or hot rolling is good. Okay, if we want to change the shape of our material, which is often the case. Okay, so in our foundry, We've cast our steel slabs or aluminium billets. That's a pretty useless shape. We want to roll it down into sheet material or something like that that's useful. Okay, so we have to do a deformation. Right? We can do it hot, we can do it cold, depending on what we're up to. Right? If these properties that we've now put into our material are no good for what we're doing, okay, we can heat the material up, okay, and we can recrystallize to a certain extent. And what we can do is then bring our properties of our material back down to here, somewhere on our curve. Right? In actual fact, because we are changing the microstructure and doing other things, sometimes we can actually pull them to here, okay, or something like that. Right? Sometimes we can get different combinations of microstructures that give us different properties. Something else that happens in a material when we deform it, rolling, forging, we put a texture in our material, an orientation of the grains. With that orientation also comes different properties. Okay, properties become anisotropic. Okay, we might want to get rid of that, or we might want to encourage that, depending on our application. So, our example here, so during cold working of material, the grain structure is essentially broken down into smaller fragments with a high defect density. Smaller grains, a lot of defects. And that's essentially what work hardening is, putting defects into our material. It actually gets stronger, okay, because it's difficult for dislocations to get around those defects and themselves. Okay, so this work hardens the material, instilling extra strength at the expense of ductility, which is what we've got in our diagram there. So also, crystalline materials often have a preferred deformation direction or plane, where deformation occurs more easily. So are we a little bit savvy on what texture is? Have you learnt about texture at all? Nothing at all on texture. Okay, so crash course in texture. We have our crystal lattice. Okay. At each intersection we've got an atom. Right. Now, if we have in our structure, depends on the deformation mechanism, okay, but if we put a dislocation into our structure, remember a dislocation is essentially an extra plane of atoms that's out of phase, so we've got to try and squeeze an extra plane of atoms in here. Okay. So here's our dislocation in our system. For this dislocation to move through our system to allow for plastic deformation, it likes to do this on a very specific plane. That's usually based on the atomic spacing. So hopefully you can appreciate in a crystal system, depending on the system, regardless of what it is, basic geometry, this distance here is much shorter than this distance here. Yeah, shorter than the diagonal. Right? The energy it takes to move an atom from this side and displace this atom is also related to the distance between the atoms. So basically what this is saying, the closer the atoms are together, the easier it is for a dislocation to glide on that plane and deform the material. So all crystals have a preferred glide plane for dislocations. What this means is, if this is our crystal, here, okay, and we're now deforming this crystal in, say, a rolling process. As the dislocation passes through the material from here to the end, okay, basically it's taking a plane of atoms from the start of our crystal to the end of the crystal. Okay, so as it's deforming, I'll just get the eraser here to try and go through it with you. We're shifting planes of atoms from one side of the crystal to the other. Right. So this crystal passed one dislocation through it, it's now changed shape. Okay, to something like this. And as this keeps happening, we keep passing our dislocations along that plane. Alright, this crystal will continue to change shape until it eventually ends up like a pancake. Okay? And that's what plastic deformation is. So the way that the shape of this grain changes with deformation is dependent on the preferred glide system of the dislocation. And what happens at the end of the day, all of those grains in the material start to orient themselves, okay, in the same direction because it's easier for them to deform in that direction. Right. So all those grains, all their crystal lattices are going to start to line up. What that does is puts texture into our material. Right. If we think about our crystal again, right, the strength of the bond between these two atoms, because of their spacing, is going to be a little bit higher. Okay. Think of our bonds again as springs or something like that. Right. So all of our springs are lined up in this direction and this direction. Okay. We try to deform our material in this direction, we're directly engaging those springs, those bonds. If we try to deform in this direction, we are engaging all of those springs, but relative to the angle that we're straining them. Okay? So basically that means that the material is going to have different properties in this direction, or that grain is going to have different properties in those directions compared to these directions. Okay? In a polycrystalline material, this becomes irrelevant because all the grains are lined up in random directions, so everything evens out, becomes an averaging effect. But after we roll it, and all the grains are now lined up in the same crystallographic orientation, okay, we end up with a material, a sheet material that might be stronger or allow more deformation or ductility in one direction compared to another. That's what texture is. So it can be a big problem, or we can use it, all right, in industry. All right. So, crystalline materials often had a preferred deformation direction or plane, where deformation occurs more easily. Often, continuous deformation will cause the rotation of grains within the material, such that they align with this preferred deformation plane. This instills a texture to the material, which can then make its properties anisotropic, which is not preferred in some applications. All right. So if we're going to have a piece of material that's going to be used in the chassis of a car or something like that, we want it to be as strong in every direction as it can be. Okay? If it has a texture, it might be very strong in one direction but very weak in another direction. Right. Texture can be favourable in magnetic applications. Okay? We all know that magnets work through ordering of magnetic moments. Okay? If we have a defined texture in our magnetic material, this is good. We can strengthen magnetic moments in particular directions, which is good for their applications. All right. But basically, recrystallization gives us the opportunity to completely or partially reverse the effects of cold work and textural evolution. We've got a couple of examples. Okay. I don't think that link's live anymore. All right. So this is where we can use recrystallization to tailor the properties of our material. All right. So all materials essentially have a recrystallization temperature. All right. But I'll say now that this temperature is not a fixed point. It's also dependent on how much deformation we put into the material. Because remember, deformation is our source for nucleation in a recrystallization process. Okay. So by definition, the recrystallization temperature is the temperature at which 50% of cold work material can be statically recrystallized in 1 hour. So this is an industrial definition. Right? So industry manufacturer, cold rolling aluminium sheet. Okay, this sheet is very, very hardened, okay, and fairly brittle because of the work we put into it. We want to recover 50% back to recrystallized grains with random orientation or texture. Okay, we would hold it at the recrystallization temperature for an hour to do that. Right, so this is kind of not a laboratory but an industrial result or experimental result. Okay, so industry manufacturers know that when they go through their rolling process, they've deformed it this much, a reduction of 50% in cross-section area for rolling or something like that. Then they know we have to hold it at this temperature for so long to recrystallize so many percent of our structure. Okay, so by rule of thumb, this is approximately 0.6 to 0.7 times the melting temperature in Kelvin. So that's usually where material will at least begin and proceed to recrystallize. Okay, so if you're doing some of the things that I do in my lab, we're designing new alloys. Okay, never been seen before. We've literally got no idea where recrystallization temperature might be. Okay, the best indicator we have is, okay, we know that it melts at 1213 Kelvin. Therefore, we've got to be within this window here for recrystallization to occur. during our processing. All right, but down here, this is our note. However, the driving force for recrystallization is an energy reduction process. So hence the driving force is strongly influenced by the amount of work the material has received rather than the temperature alone. Okay? So different materials and crystal structures respond in different ways. Okay? So there's this codependence. If you've only deformed your material a little bit, that means there's fewer nucleation sites for recrystallization to occur, and we'll get onto the sites themselves in a moment. Okay? Which means you might have to choose a higher recrystallization temperature to get things moving, right? Or sit it at a temperature for a longer period of time. Okay, so hopefully we're starting to appreciate that the kinetics of recrystallization is dependent on a few things. How much deformation, pre-existing deformation, the temperature we're holding our material at, and then the time as a consequence. Okay. So the empirical laws of recrystallization, again associated with the recrystallization temperature. All right. So recrystallization, it is thermally activated. All right. We need to go to elevated temperature for this to occur. Also remember, we're talking about absolute zero here. Okay. Some materials have crystallization temperatures close to room temperature, and they might recrystallize very close to room temperature if they've got enough deformation in them. All right, we're talking in Kelvin. So the kinetics of the atomistic mechanisms controlling nucleation and growth of recrystallized grains depend on annealing temperature. Okay, and this is an Arrhenius relationship. So remember, kinetics is equal to temperature and time. So in terms of the critical temperature, okay, there's also a critical temperature. Recrystallization requires a minimum temperature or an activation energy for the necessary atomic mechanisms to occur. Okay, so for a given fraction of recrystallized grains, recrystallization temperature decreases with annealing time. Okay, there's also, in terms of activation energy, okay, there's a critical temperature where atoms become mobile. So this is still a diffusion-based process. All right. So at room temperature, for something like copper or even aluminium, recrystallization, despite how much deformation you might put into the material, may not occur. Right? May not start. It's because at that temperature there's not enough energy for atoms to become mobile. Okay? Atoms also need to be able to diffuse to grow those new recrystallized grains. Okay? So this is why deformation and temperature are important to recrystallization. There's also a critical deformation. Okay? So the prior deformation applied to the material must be adequate to provide nuclei, remember this is still a nucleation-based process, and sufficient stored energy to drive their growth. Okay? So if you pass a small degree of deformation over your material, and again, in terms of our stress strain curve, if you move up here to only this point, just starting to plastically deform, and there's probably not enough deformation or stored energy in the material to nucleate regions, okay, for recrystallization to occur. Or enough energy stored in the structure to drive recrystallization. Okay, so after saying that there's a critical temperature, we come back to this point, or this codependence. Okay, so deformation affects the critical temperature. So by increasing the magnitude of prior deformation, okay, so we can think about this in how much we're reducing our sheet material when we roll it, 50%, 60%, 80%, okay. Increasing the magnitude of this prior deformation, or reducing the deformation temperature, will increase the stored energy and the number of potential nuclei for recrystallization. So as a result, the recrystallization temperature will decrease with increasing deformation. Okay? So the driving force is coming from deformation. The activation of the processes for recrystallization come from temperature. So the more deformation we put in the material, the lower the recrystallization temperature. So try not to make this too confusing. Okay, but the temperature at which we work our material is also a little bit important. Cold rolling versus warm rolling versus hot rolling. Okay? As we heat a material up while we're doing our deformation, okay, that temperature allows the number of defects we're creating to be a little bit less. Okay? Material can flow more easily at elevated temperature. Okay? That's because atomic bonds can be dissociated more easily at elevated temperature. It's easier for dislocations to glide at elevated temperature. We've also got the precondition of our material, or the pre-structure. Okay? Is it an as-cast material? Has it been annealed for 1 hour? Has it been solution heated and annealed for 24 hours? Okay? So the initial grain size or crystal structure of our material also matters to recrystallization. All right, so initial grain size also affects critical temperature. Grain boundaries are good sites for nuclei to form, and we'll show this in a little minute. Since an increase in grain size results in fewer boundaries or intersection points of grains, this results in a decrease in the nucleation rate and hence an increase in the recrystallization temperature. So our prior grain size of our material. If we've got a material with very, very large grains, there's fewer sites for new crystals to recrystallize from. Okay. Often this is happening at intersections of grains. Okay. We've also got to be wary that deformation affects the final grain size. So increasing the degree of deformation, okay, so again, use the example, 50% reduction, 60%, 80% reduction of our rolled material, or reducing the deformation temperature increases the rate of nucleation faster than it increases the rate of growth. Okay, so this is a little bit of a tricky one. So if we do a large reduction, okay, we've essentially created more nucleation sites for our recrystallized grains. Okay? More dislocations, more defects, more grain boundaries that are intersecting through a higher deformation compared to a lower deformation. Okay? As recrystallized grains start to grow, if there's more nucleation sites, more grains can grow at the same time. And what happens is they impinge on each other more quickly. Okay? So if we have a very, very high prior deformation, means the driving force is very, very high for recrystallization. We've also created a greater number of nucleation sites for nucleation of recrystallized grains. If they all start to grow at the same time, which they will, okay, they will grow quickly and then quickly impinge on each other and stop. So we're left with a finer grain size material. Finer grain size material still has a higher degree of internal energy or structural energy than a large grain size material. Okay, so our end materials, something that's had a small deformation compared to a large deformation, after the recrystallization process, the one that had the higher deformation will have a smaller grain size and probably higher strength and lower ductility. Okay, so it's a complex story for recrystallization. All right, all these factors are kind of interrelated and codependent on each other. How much deformation the material's seen, what did it look like before we started deforming it, okay? What temperature and time factors we're putting into our recrystallization process. All right. So far we've really only spoken about a static recrystallization process. Okay? Static means we've taken our material, we've deformed it, then we go and put it in an oven, heat it up and recrystallize it. Okay? So a two-step process. Deformation, heating or heat treatment that leads to recrystallization. All right? So static recrystallization after a cold working event, a material may be subject to a heat treatment above the recrystallization temperature to partially or fully recrystallize it. So this is generally a very controllable process where optimal desired microstructures or properties can be achieved. Okay, so static recrystallization can also occur after hot working, but basically after a cold working event, we know we've instilled a 50% reduction, for example, on our material. Okay, so that's no longer a variable, and we can repeat that over and over again in a rolling mill. for example. Okay. We then take our strip that we've rolled, we subject it to a fixed temperature for a fixed amount of time. Basically, our products at the end of the day are going to have plus or minus 1% the same properties. Yeah? So static recrystallization, easy to control, two-step process. We also have a process known as dynamic recrystallization. Okay, and this will make sense. Okay? So often, plastic deformation is carried out at elevated temperatures. Okay, so we think of our steel rolling mill. We don't usually roll steel at room temperature. This is usually done above the austenite transformation temperature, 900, 1000 degrees, glowing red hot, white hot. Okay, that's because the stress is required to change the shape of our material much less at elevated temperature. Right? But we've got two things going on, haven't we? Okay, so we're deforming the material. We're breaking down the grain structure. We're putting dislocations into the material. But at the same time, we might be above the recrystallization temperature. So the two things are happening at the same time. We're creating defects, vacancies, dislocations, breaking down grain structures, grain boundaries. Okay? Then almost instantaneously, we're recrystallizing new grains because we're above the recrystallization temperature. This is called dynamic recrystallization. So, yep, we carry out our deformation at elevated temperatures to reduce the flow stress of the material. Okay, reduces the energy required for the deformation process and for dislocations to glide, making it easy to deform. This is often above or close to the recrystallization temperature. The combined effect of deformation as well as energy associated with deformation and temperature often places the material in a cyclic state of grain refinement and recrystallization. Even though this is a little bit harder to control, right, it is a manageable process of achieving ductile or larger grained or textureless materials. Okay, so again, basically through industrial experimentation or lab experimentation, okay, we can say, all right, if we take our material, if we're progressively reducing the thickness, okay, so think of a gang rolling mill, this set of rollers takes it down to 90%, 80%, whatever else. Okay, it's a certain amount of deformation at a given temperature each time. We know at our endpoint we will have recrystallized X amount of grains, maybe 100% of the grains, and they will have a specific grain size if we keep our process the same. And we can start to model this process. So it's just a mathematical model. Very hard to bring things like thermodynamics into these sorts of models or outputs. Okay, to give us a final grain size and a fixed property profile of our material. Alright, so let's have a look. We've got a couple of videos here. We'll play these videos and then we'll take a break. A couple of videos of dynamic recrystallization. Let's see if they're any good. Okay, so the deformation rate here is quite slow, but we can see our grains are changing shape. Okay, and we can see from the interiors of these grains, we can't really see the deformation occurring. We can see shadowing and ghosting going on in these grains here, these large prior grains. But these new recrystallized grains are forming and growing constantly during the deformation process. Some of them from within one another. Okay, so one's just happened from inside of these two here. Okay, so we've got this constant process of breaking the grain size down, growing new grains, they're breaking themselves down, growing new ones from them. Okay, so it's this dynamic process that's what's usually going on in a hot rolling process. Okay. The second video here is from the same authors, very similar. But happening at a very slow rate. So we can start to see new grains forming and growing at the boundaries and interstices of these prior grains. There's a couple here that have been growing as we're deforming the material. Okay. The orientation of those new grains is typically very different to the parent grain. Okay. It's actually a condition that those orientations are different for them to grow. Otherwise, they just stay there as a single broken down grain within the grain structure. Okay, so we'll take a break now. We'll give it 10 minutes and we'll start up again. Okay guys, we'll get started again. Okay. So what I'm going to show you now is an industry example, okay, of recrystallization. Okay, so here at UNSW back in 2012, 2013, I was working on a project with Volkswagen. Okay, Volkswagen are trying to use strip cast magnesium products. So we cast sheets of magnesium 1.2, 2 meters wide, 3 millimeters thick through a set of rollers to get it very, very close to its final shape. Okay. Then what we do to that strip is we roll it, okay, get rid of any casting defects or anything like that, and to try to increase the strength of that material, reduce the grain size. Okay, HCP materials, the grain size is also a little bit critical for ductility because we have grain boundary sliding going on as well. Right. So what part of my job was there was to define a rolling program to do that reduction, okay, easily. The magnesium is a fairly brittle material. You have to get at elevated temperatures at fairly low reduction rates to do the rolling process, hot rolling process. Okay, but again, very close to the activation energy when atoms become mobile enough for the material to be very ductile. It's going to be very, very close to that recrystallization temperature. Okay. So what we've got here, okay, are some of our microstructures from the rolling process. Okay, so we can see here directionality in this direction. Okay, these materials were hot rolled at 320 degrees centigrade, a reduction of 50% from 3 millimeters down to 1.5 millimeters. Okay, so that was fixed. Okay. When rolling at 320 degrees Celsius, we went and did an analysis using EBSD on the texture of the material. Right. Now, texture in these types of plots is represented by colour. Okay. Basically, what this diagram is showing us and what these diagrams here are showing us, we can see a concentration in certain positions on different crystallographic axes of data, okay, or grain orientations. Okay. So majority of the grains that we can see in this structure are green or blue. Right? It's not random red, yellow, green, blue. Okay. So that represents or shows us that the orientation of most of these grains are very similar to one another. Okay, so they all are lining up. These are deformed grains that have deformed. Just like a process like this, they've oriented themselves and have produced a rolling texture. Okay. We have a look down here in the corner. These are the results of our tensile test. Okay. So when we've rolled down this strip material, we've cut a tensile sample out of it and we've strained it. So what we can see, that we've got a yield strength of 250 megapascals, which is fairly high for a magnesium alloy. Okay, again, due to this fairly fine grain size, okay, we're down to 3 to 5 microns in some cases. But we can see that only after about 3% strain, this material has broken and failed. Okay, so despite having a very high strength for a magnesium alloy, which is favourable, the ductility was terrible. Okay, 3%. You can't do much deformation, or this material can't take much load or fatigue or anything like that with only 3% ductility. So particularly for an automotive application, that's a fairly useless material. Okay, it's undergoing dynamic strain conditions all the time. Yep. So take note, that was at 320 degrees centigrade. Here, when we've increased our rolling temperature to 350 degrees centigrade, we've got a very different result. So straight away we can see, okay, we do have some larger grains here that aren't showing any deformation. The colours of these grains here are more in the red to purple range, which is actually showing they're less oriented in the basal plane or the prismatic planes for magnesium alloys, which is a little bit beyond what you guys need to know. Right? But we can see a very, very different map here. We do have green, we do have yellow, we do have red, we do have pink, got a little bit of blue in there as well. Okay, slightly larger grains. Right? We can see these are larger. But we can also see that we've lost a lot of the directionality of rolling that we saw in the last sample. Okay? This is due to, of course, dynamic recrystallization. Shifting from 320 degrees up to 350 degrees, we've exceeded that recrystallization temperature by some amount, and we're getting dynamic recrystallization occurring in this process. Okay, so there was no post-heat treatment on these samples. We can see from our pole figures here that we don't really have those localized spots in these two planes anymore. It's actually very random where these spots are occurring. They're at different places compared to the other one if they are localized. Okay, and on our basal plane we are getting a slight concentration. So we've changed the texture of our material through recrystallization. And here's the result. Okay, so here now we've got a yield strength of about 225 MPa. So remember the last sample was about 250. We've lost a little bit of strength, but that's okay. When we do our tensile test, we can see that we've got almost 20% ductility. Okay, so this extreme change in properties. Yep, we've lost 25 MPa in our yield strength, right? But we've actually gained something like 15% ductility, which is exceptional for magnesium, or just highlights the important role that texture plays in the properties and performance of our alloys. Okay, so simply by changing that hot rolling temperature, we change the properties of our material that's coming out the other end. Okay, this material under these conditions is what would be then used, okay, in an automotive application. All right. All due to dynamic recrystallization or recrystallization. Okay, so there's an application. Hopefully you can appreciate the importance now of this process. Okay, so there's the side-by-side comparison, okay, with the scale bars all matched up. So slightly larger grain size, high percentage of recrystallized grains going on there, and this is the difference in mechanical performance. All right. This next section, we're going to be talking about nucleation in recrystallization. What is the mechanism? How does it actually occur? I keep telling you that it's deformation driven, and dislocations are involved, but how are they involved? Okay. So originally it was assumed that the nucleation rate of recrystallization, okay, would be determined by the thermal fluctuation model, or classic nucleation theory, which we've already studied. Right? But that's actually not the case. Okay, people have tried to fit it, it doesn't work. Okay, that's because the mechanism here is driven by deformation, not by temperature fluctuations. Okay, and structural fluctuations like in classic nucleation. Okay, so the observed recrystallization nucleation rate, okay, was 10 to the 50 times greater than what's calculated by classic nucleation. And 10 to the 50 is a big number. We can't fudge that. Okay, so obviously the mechanism is very, very different. Okay. So the problem was that the stored energy due to dislocations is fairly low. Okay, a few joules per meter cubed, while the energy of grain boundaries is quite high. Okay, so the nuclei which give rise to recrystallized grains are not formed during annealing; they're actually already present in the deformed state. Okay, so the deformation is already programming into our material where our nucleation sites are going to be. They've already been born, okay, due to the deformation. All right. So recrystallized grains, they don't nucleate in the classic fashion, but grow from pre-existing nuclei or cells and subgrains that result from the local accumulation of dislocations. So we'll talk a little bit about what dislocations are. Okay, for you at this point, they're kind of like a squiggly line that we know is a crystal lattice defect in our material. Right. So what happens is, okay, when we're deforming our material, we've got dislocations running through it everywhere, often in certain directions. Okay, when they hit a grain boundary, these dislocations get entangled with the grain boundary. Okay, they are a crystal defect. If the next grain along over the grain boundary has got a different orientation, okay, or the grain boundary just being a random jumble of atoms itself, so that dislocation can't really proceed now. It gets jammed at that grain boundary. It stops, okay, and that grain just continues to change shape. All right. Often, at a grain boundary or the corner of a grain, the intercept of multiple grains, we can form cells of dislocations. Okay, so this might be a specific crystallographic orientation that we're forming a high concentration of these dislocations. So when dislocations come across one another, they can get tangled within each other. All right, and they hit a grain boundary, they stop. Then another one piles up behind it. It's just like a big traffic jam in there. Okay, and in certain cases and scenarios, they will be localized because of this tangling process or traffic jam process that's going on. Okay, what this localization of dislocations is, it starts to form this cell. And this cell of material starts to behave independently of the parent grain. All right. Sometimes the atoms within that cell can start to rearrange themselves or rotate during deformation. So if one of these subgrains in a local area happens to have an advantage over its neighbours, such as a locally high dislocation density, a greater size or favourable crystallographic orientation, then a new strain-free subgrain will be able to grow more rapidly than surrounding cells. Okay, so over time, right, these particular cells here, some of them have got a higher dislocation density. These dislocations will continue to move to the walls of these cells, and we start having an individual region that's encompassed by these dislocations. These dislocations start to line themselves up a little bit more properly over time, okay, forming cell walls like this, which are essentially the nucleus or nucleation site for our new grains. Okay, these dislocations can then start to move away, okay, become grain boundaries. The material in here can start to rotate compared to the parent grain and create essentially what is a new grain. Okay. A tricky process, still not fully understood, but it has been observed. Okay. Okay, so here's just outlining that process again. All right. So as these boundaries become more and more misorientated, okay, at high angle grain boundaries with respect to the surrounding material, it can then be recognised as a new strain-free grain. Okay, so the dislocations have moved out. This region is acting independently of the rest of the grain that it's in, okay, and we've started to form a new grain. This is how recrystallization is nucleated. Okay, high concentrations at dislocations at certain points. Okay, so now hopefully you can appreciate that the more deformation we put into the material, the more dislocations we're generating. The more dislocations we're generating, the more of these subcell structures can start to form, which are the nucleation sites for new crystals. Okay, so it's driven by deformation, how much deformation the material's seen. If we don't have enough dislocations to form these cells, then we won't form the nucleation sites. Okay, we can't recrystallize an annealed material, for example. We can only grow grains in an annealed material. It has to be a deformed material. So here's some real life examples. So this is under the TEM. Okay, so this here is a semiconductor, right? It's been deformed or undergone strain. We can see here, now with semiconductors, the bonding is a little bit more covalent, right? So we get high directionality. So our dislocations line up in some very, very specific cell structures within our major grain. So here's the wall of our major grain here, and here, we can't see the rest of it. This is in the interior of a single grain after deformation. So all the dislocations are lining up on specific planes, trying to cancel each other out, okay, and minimize the structural energy. This is why they form in these specific patterns, okay. With more deformation or with heat, okay, regions, some of these subcells, probably one of these ones here that's smaller, might orientate itself a little bit differently. With a bit of temperature, this might start to grow and consume the rest of these cells. Okay. Here's an example in metals. Okay, so all these squiggly little lines that look like a bit of cotton wool or hair on the microscope lens. Again, this is under a TEM. Okay, we can really only see dislocations in a TEM, not an SEM. Okay, we can see they start to get tangled up with each other and form these subcells. Okay, one of these subcells, maybe one of these ones over here. Okay, we can see here we've actually got a grain that started to recrystallize here. Okay, within this other major subcell. So that's how they form. We need those dislocations, we need them to tangle up, form those subcells within our grain. Those subcells start to realign themselves and reorientate themselves dislocations are cancelled within their core and they start to grow as a deformation-free crystal. All right. So, a little bit on thermodynamics, or trying to apply thermodynamics to this process. Okay. So the driving force for recrystallization. Okay, and here we just take it as a difference in the energy between the deformed and the recrystallized, or the strain-free state. Okay, a delta E, change in energy, which can be determined by the dislocation density or the subgrain size and boundary energy. Okay, boundary energy is very, very hard to measure unless it's a single plane. We do approximations there. Okay, but as you can probably appreciate, we measure the subgrain size, we measure the dislocation density, okay, through visual means, okay, lab measurements, and try to fit it to our equations to define the processes. Okay, so here rho is our dislocation density, G is the shear modulus of our material. So again, this is a deformation or a material property or response to deformation. B is the Burgers vector of the dislocations. So this is the size of the dislocation step. Okay, Burgers vector typically is half the atomic spacing of the crystal lattice. Okay. And we say that this is approximately also equal to 3 times the subgrain boundary energy and the subgrain size. Okay, so we're equating measurable properties with energetic properties, and something that we can measure. Okay. And I'm not expecting you to memorize these equations. So, recrystallization kinetics, okay, follow a profile like this. Okay, often there's this initial nucleation period. Okay, as we're heating our material. Okay, trying to make things recrystallize, and then they begin to grow at a constant rate. Okay, so basically the growth stage here is a constant. This is based on basically diffusion of atoms adding to the surface of the new defect-free recrystallized grain. Okay. As we approach the end of the completely recrystallized process, okay, we slow down again. This is because the grains start to impinge on each other. Okay, growing grains, growing recrystallized grains will start to touch each other, and basically the two energies of those defect-free grains are equal, right? So they don't take over one another too much. Right? The rest of this process is just filling in the spots where the grains haven't touched yet. Right? This was described, and I don't think I'll go through this equation here. It's just very, very basic of how nucleation rate is defined by an initial nucleation period, defined by T0, and a total time, okay, and the rate of change of the size of the grain, something that we're measuring physically. Right? I'll just note, though, that this was defined by Humphreys and Hatherley, okay, as late as 2004, so that's pretty recent when we talk about metallurgy. Okay, Hatherley was a professor in our school just here. All right, so this initial nucleation period, T0, okay, is related to factors mentioned previously, such as the amount of deformation, okay, so the inherent dislocation density, or nucleation, number of nucleation sites of the material. Okay, so for a material that's got very little deformation, okay, this curve will shift a long way to the right. T0, the time to the onset of crystal growth, is going to be much, much longer. However, if we've got a heavily deformed material, all right, this nucleation rate is going to be much, much shorter. Okay, more deformation, more nucleation sites, higher driving force for recrystallization to begin. Okay, and as we've mentioned already, the growth rate is more closely connected to temperature. Okay, so again, hitting that critical recrystallization temperature, all right, and diffusion of the atoms to the new grain surface. Okay, so remember, diffusion is also interrelated with temperature. Higher the temperature, higher diffusion rate. Okay, you have a critical temperature where diffusion just doesn't occur. Okay, there's an activation energy for diffusion, which you would have covered with Rakesh, yeah? Alright, so hence, heavily deformed materials will crystallise more rapidly than those deformed to a lesser extent. We've covered that. Okay, deformation at higher temperatures will allow concurrent recovery. So this is recovery at higher temperatures is basically the annihilation of dislocations. and hence these materials will recrystallize more slowly than those deformed at room temperature than annealed. Okay? So hot rolling close to or above the recrystallization temperature basically is giving us fewer nucleation sites. Right? So our nucleation rate and recrystallization rate for a material deformed at elevated temperature, cooled and then heated again, is going to be slower. Okay? Because the high temperature processing annihilates a lot of those dislocations. Okay. So if we want to maximise recrystallization rates, right, cold working is the way to go. We're creating a lot of dislocations, a lot of grain boundaries and defects, hence more nucleation sites. Okay. Other influences on recrystallization. Okay, so we've already learned, I'll just pull that back. We've already learned through classic nucleation, okay, two different cases, homogeneous and heterogeneous nucleation. Okay? Heterogeneous nucleation, we're providing a site that has a lower energy for the nucleation and growth of a new phase, okay, an inoculant or something like that. Okay. We see effects by having other types of materials in, so other elements or defects or chemical fluctuations in our material on recrystallization. Okay, so additions or impurities have a strong influence on recrystallization kinetics. All right. So even minor concentrations can have a substantial influence on recrystallization temperature. It's currently unknown whether this is due to the retardation of nucleation or the reduction in the mobility of grain boundaries. Could be both. All right. So basically, if we have a solute element, something that we introduce to our metal, okay, typically it's dislocations will become tangled or hooked up on that solute element as they're trying to pass through our material. I don't have another colour here today, but right, basically, if we have a different size atom on a side, that imposes strain fields in the lattice. Dislocations are also putting a strain field in the lattice because they're a defect. Okay? Defects will attract one another to try and cancel out those strain fields, so dislocations become attracted to defects. When they're attracted to defects, they're hard to pull away from defects. Right? So by decreasing the mobility of dislocations, we're kind of decreasing the rate at which they can start to form those cells for recrystallization. Okay? So having solute atoms in a system, we can actually alter the recrystallization kinetics of our material. And we can engineer materials to do this if we don't want recrystallization to occur, or we can try to remove specific impurities that do the same effect. So that's solute atoms. They're a lattice defect, an atomic size defect. Large particles or precipitates are something different. So a different phase or an inclusion of an oxide or something like that. Okay, so particles of different sizes can influence recrystallization kinetics in different ways. So small, closely spaced particles. Okay, so if we're on purpose precipitating out a phase for strengthening in our material to slow down our dislocations, what we're also going to probably be doing is affecting our recrystallization pathways and kinetics. Okay, so small, closely spaced particles tend to affect dislocation motion and pin grain boundaries. Okay, so this is another critical factor. If we've got a particle sitting on a grain boundary, it's hard for that grain boundary to migrate and grow around and encapsulate that particle. Okay? And recrystallization is all about growing new grains which have boundaries. So if we've got particles everywhere, it's very difficult for those grains to continue to grow or even nucleate because of those particles, particularly if they're very, very fine and very evenly spaced. All right. So this opposing driving force arises from dislocation density and their influence both nucleation and growth kinetics. Okay? Having those particles there, finely spaced, very, very small, can change and largely retard our recrystallization kinetics. However, large, stiff particles, okay, in our material are a little bit different. All right. So these induce their own deformation fields or stress fields in the lattice and can often contribute to the local generation of dislocations, which can enhance recrystallization effects. So if we've got a large chunk of something that's quite stiff in our material, all right, as we're trying to deform our material, we've got this mismatch in mechanical properties. Okay? Let's say that our chunk of material is very, very stiff and very, very hard, and it's sitting in a nice ductile metal. The metal matrix around it wants to move and deform. However, it's trying to stop it. So what this does, creates an inverse strain field or force back on the matrix. Okay? So the particle not wanting to deform and the matrix deforming around it puts extra stresses and stress concentration in our system. And that extra stress and stress concentration and localized deformation creates dislocations. So these big stiff particles can be an extra source of dislocations. Right? When we're starting to create extra dislocations or sources of dislocations, okay, we can create more of these cells, which are the nucleation sites for recrystallization. Okay. So small particles, pin boundaries, make it difficult for dislocations to move about, slow down recrystallization kinetics. Large particles create a stress field, creating more dislocations, which enhance recrystallization kinetics. Alright, so we've talked a lot of stuff and a lot of theory. Can anyone think of why we might want to actually enhance recrystallization? The rate of recrystallization in the material? Through the introduction of impurities or large particles or something like that? Why would we, working in industry or making a product, want to enhance recrystallization? Right, so one instance, property control. So a uniform dispersion of strengthening particles can lead to a more uniform recrystallization and a finer recrystallized grain structure, which is often favourable. So small grains give us our higher strength. If we've got a random texture in there, this is also very good. So property control is one reason. Key one over here, dollar signs. Okay, if we can enhance the recrystallization rate, and recrystallization is a part of the process we want instilled in our end product, then that means we don't need as much deformation, so less work by our rolling mill or our forge, and we don't have to go to as high a temperature for as long, saving electricity in our furnaces. Okay. So enhanced recrystallization by large particle dispersions can reduce recrystallization temperature and time during processing. Improved hot or warm workability. So enhanced recrystallization kinetics, in particular dynamic recrystallization by hard particles, can reduce the work hardening of a material during hot or warm rolling cycles. Okay, and this reduces the load required for deformation. Okay? So by minimising the work hardening that's going on during our process through controlled dynamic recrystallization, we can reduce the load or the amount of work our rolling mill is actually doing. Again, saving money, making for a faster process. Alright, so that was the arguments for. Why might we want to stop recrystallization or slow it down? Anyone know why we might want to stop recrystallization? So, what's recrystallization doing to our material? We're getting rid of all prior deformation. It's going to be raising our yield strength. Okay. Maybe we need a material that is inherently strong or stronger. Recrystallization is going to keep pushing us back down here. Okay, so if we don't need a great deal of ductility and we actually need higher strength, we don't really want recrystallization to happen too much, do we? If we put cold work into our material to make it stronger, sometimes we want to keep it strong. Okay, T3 and T6 tempers in aluminium alloys are a key example. Okay, increasing that strength of the material so it is useful. So, microstructure retention during elevated temperature service or tempering. Right, so many materials are cold work to reduce or refine the grain size and particle distributions in order to enhance mechanical strength. Often we do, following these processes, a very, very low temperature tempering process, just to take out a little bit of strain, okay, and recover some ductility, okay, by the annihilation of some prior dislocations. This is called recovery. Right, so this can be done more effectively if recrystallization is slowed or arrested, typically by fine particles, and also limit grain growth for higher temperature applications. Okay. So if our material is going into service in a warm or hot environment, if the grains start to grow and recrystallize in that environment, we're changing its properties while it's in service. We might be reducing its strength in service. Okay, so it might fail if it continues to recrystallize. Another one that's becoming a key technology is superplastic forming. So we've spoken a bit about superplastic forming of viscous materials like our glasses and our polymers and things like that. Right? Superplastic forming can be done with crystalline materials to an extent, and it requires a really, really tiny grain size. Okay? So the deformation process in superplastic forming isn't dislocations, it's grain boundary sliding. All right? With recrystallization and grain growth, grains grow big, our grain boundary surface area becomes smaller, okay, overall, compared to a very fine grain size, so we can no longer superplastically deform the material. And we can't do this forming process. So there's a quick slide here about superplasticity, okay, and the things that get made using superplastic forming. Right, so superplasticity is a state in which a solid crystalline material is deformed well beyond its regular breaking point, usually in excess of 200%. Okay, so we saw a tensile test sample there of magnesium, 20%. That's very good for magnesium alloy. 40% is exceptional for an aluminium alloy. Okay, but under the right conditions, okay, the right grain size and the right temperature combinations, we can get elongations of up to 200% in these materials. Right. It's usually done at elevated temperatures, okay, required to allow recovery and minimise work hardening. Okay, so we're kind of minimising the effect of dislocations and things on work hardening. Okay, and we're just keeping these grains all the same size. The deformation mechanism is the actual grains sliding around one another. So it allows for the production of large, intricate parts where large deformations are required that are unachievable by conventional alloys. Okay, so here's a titanium superplastically formed part. Okay, this type of structure in a single piece, it's in two pieces here with the join here, but these structures and substructures here, we cannot produce with a typical crystalline material because we exceed their plastic deformability. Okay, we exceed this tensile test curve. Okay, we hit our failure point. All right, so we can form things like this out of materials that typically can't do these large deformations. Okay, so very, very large elongations. So with superplasticity, again, the precise mechanism is very complex. Okay, we don't fully understand it at this point, and it's inevitably going to be different for different materials. Right? But the major contribution to superplastic effect is grain boundary sliding. Okay, so our grain boundaries will slide over one another instead of dislocations, activating to accommodate strain. Okay, so it's not necessarily associated with dislocations. There's a couple of videos there. I think I'll let you have a look at those in your own time. We've got time for one. We'll look at grain boundary sliding very quickly. Okay, so just a model of how grain boundary sliding would work in a granular type system. Okay, pretty basic. Okay, so that's how these materials deform. Right. So they're undergoing large strains and things like this at elevated temperature. Okay, often we're going to be very close to the recrystallization temperature. So we actually have to engineer these alloys very specifically. All right. So the example here is superplastic forming in aluminium alloys. All right. What we do with our aluminium alloys is we add some very specific elements, things like zirconium, or rare earth elements like scandium, yttrium, gadolinium, things like that. What happens when we add those elements to our alloy? They produce a precipitate particle. Okay, typically something like an aluminium-3 zirconium or an aluminium-3 scandium particle. Tiny little particle. What those particles do is sit on our grain boundaries of our material, our ultra-fine grain material, and they stop the grains from actually growing. Okay, so recrystallization during deformation, okay, isn't happening, partly because we've engineered these really fine particles sitting on grain boundaries, stopping recrystallized grains and existing grains from growing. If they did grow, like I said, surface area, total surface area of the grain boundaries there will be reduced, and we will lose our superplastic forming ability. Okay, so we need to retain very small grains at high temperature for superplastic forming processes. Okay, and to do that, we minimise or stop our recrystallization processes by having these dispersions of very fine particles. All right, that's it, guys, for today's lecture. Okay, hopefully you now know all about recrystallization. The black and white set of slides isn't available for this particular lecture. I'll modify that and upload it this afternoon for you. Okay. Just for people that like to print reams of paper with the slides on it, that's all.
Good.